Hi guys, this is Duncan from dunksblog.com and it's time for a tutorial. Today we're going to talk about RAID, redundant array of inexpensive disks or redundant array of independent disks, depending on who you speak to. And RAID allows you to have a group of physical disks provide itself as one logical disk on your system, with having magic going on in the background. So you can have increased speed, you can have fault tolerance, you can have redundancy, all that sort of stuff all going on in the background, but you're only seeing one area of usable space in your operating system. Now, there's several different configurations and levels, and there's hardware and software based versions. I'm not going to talk about those. I'm going to talk about the RAID levels that you can have today. And I have RAID 0, 1, 2, 3, 4, 5, 6, and 10. Now 10 is a nested RAID level, or a hybrid RAID level. There's also RAID 100, 50, 51, 53, a load of them, but I'm only going to go through the basic ones, 0 to 6 and 10. Even then, some of those are pretty obsolete now, but it's worth knowing anyway, and the nested ones are combinations anyway. So, without further ado, let's get started with RAID 0. RAID 0 uses a form of striping, and there's three different versions that are used really in RAID. There's bit striping, byte striping, and block striping. What it generally means is splitting data up across multiple areas. So as you can see here, if you can imagine these to be physical hard disks, these little cylinders here, and my data is on these physical hard disks. Imagine that they're 1 terabytes each, and going on, they're all going to be 1 terabytes each. And my data is on here. Now, A1, A2, A3, A4, A5, A6. Imagine that's a table in Excel or something like that. It's spread across this disk. Why is that done like that? Well, the advantage of that, if I was to say for a person to write down A to Z on a piece of paper, it's going to take them some time. If I then ask two people to write A to Z, but one of them to write A to M, and the other person to write M to Z, then that's going to take a lot quicker time than it is for one person to write A to Z. And that's the advantage of having two drives. You get much faster write performance. But if I was to kill one of those people, so if I killed the guy writing A to M, I've lost the alphabet and I need the alphabet. So if you were to take out one of these disks, or one of these disks died, you've lost all of your data, and because it was treated as one logical drive, you're not going to access your data, it's gone. That is pretty much RAID 0. So not ideal for a mission critical system, but provides speed increase. So this one is RAID 1, and if you can imagine my data is on the left hand side, A1 to A4 on this terabyte hard disk. It's got itself duplicated over to disk 1, A1 to A4. So what this means is that I will not have as much space as I'd like with my 2 terabytes in total. I would only have 1 terabyte of usable space, but I will have the reliability of if disk 1, for example, was to fail or die, it could, or the RAID controller could simply move over to the working version. I could then put a new hard drive in and it would then start duplicating itself again onto the new drive. So this is ideal for reliability. Performance won't be affected because it's effectively only going to one of the drives. Well, maybe with a hardware RAID controller, some of them have a cache that you might be able to use, which may have a small performance boost, but this is mainly designed for reliability. So now on to RAID 2, and this is a little bit more complex and it does require a minimum of 3 drives. So here we have 4 terabytes of usable storage, so 4 different drives, and my records are put across all of them. My data is striped at a bit level, so that means that the drives need to work in a certain way. I believe, I'm not going to go into the technicalities, but they have to work in a certain way for them to all work together in the striping. And we also have 3 dedicated drives for error correction. So what that means is that when data is written, it will calculate the error correction code, also known as Hamming code, or ECC, and it will then write it to these disks. But when it comes to reading from the disk, it will then need to read the corresponding code, and then if any adjustments need to be made, it will do it on the fly. So you may get that sequential read and write performance benefit by having these all working together. Random will not have a benefit, but you do get the error correction. But with RAID 2, it's not really available anymore. Nobody uses it. Error correction is in hard drives nowadays anyway, so it's a very old, obsolete solution, but it's good to know how it works. So we have that 4 terabytes of usable space and 3 here, in this case, dedicated to error correction. So RAID 3 involves storage using striping with bytes, which similarly to RAID 2 requires some synchronous between the disks. These all have to spin in sync for it to store. And it also contains a parity disk. Those parity bits are stored in here, and they're rules that can define information on the records that are stored on the other 3. So you'll have 3 terabytes in this case of usable storage, and then the extra parity disk, which can contain rules. So if disk 1 was to die, it would be able to reconstruct that disk based on the records it has and the rules it has. I won't go too technically into parity, but it works that way. It needs a minimum of 3 drives to operate, and you'll get good sequential read and write because these are working synchronously, but random read and write will have worse performance. So this might be good for large video editing, but again, this is not a commonly used method. It's just something to let you know how it works. So it's a dedicated parity disk, 3 data disks stored on a byte level, synchronous. Here we are with RAID 4, which kind of performs similarly to RAID 3. RAID 4 is actually stored or striped at a block level and has that dedicated parity disk. So you're looking at good random reads because the data blocks are striped, and bad random writes because for every write it has to write to the parity disk, so you are getting that slight delay when you're doing that. It's far more efficient to go with what we're going to talk about next, which is RAID 5. This is something that's not very commonly used, but it doesn't require that spinning in sync. But yeah, let's go ahead and talk about RAID 5. So here we are with RAID 5, and this time instead of having a dedicated parity drive, which would make you lose a terabyte of space, over here we have distributed parity, which again will allow you to lose a terabyte of space, but you can actually have more space efficiency here by storing across all of the stuff. So again, if disk 1 was to die, you could replace that disk and it can get reconstructed by the missing records that are available on the other drives and through the rules of that parity disk. So this is probably the most cost-effective solution. You do lose that space, but you get good performance too because it is doing block level striping. And yeah, write operations might be a little bit slow because again it does have to write that parity information, but it's pretty good for things like databases. And here we are with RAID 6. This gets a little bit more complex. This is actually dual parity, so you're having essentially 2 parity dedicated disks distributed across all of your disks. Now this is probably more useful if you have a lot more disks than is shown here, because 2 disks can actually fail out of your entire setup. You can replace those, and again, using those parity rules and all the records that are available, you can then get them replaced and it will be efficient. So again, can handle 2 disk failure. RAID configuration is complex though, and yeah, that's used through the block striping system too. And here we are with RAID 10, which is also known as a nested level 1+0. The reason for this is because we have a RAID 1 setup, in which I talked about before, where you are mirroring data, but it's then striped across. So in this case, for this disk here to die, your system won't screw up because you have that backup with the first drive in RAID 1. And it's also giving you the level of performance with the RAID 0 stripe, but it's only giving you half the usable space in this case. So this 4 terabytes here would only give me 2 terabytes, but it's a very efficient solution because if you're adding more drives, an entire pair of drives would need to fail in order for this drive to mess up. Because it's a nested level, and then you have that entire RAID 0 giving you that added performance that you'd require. So this is a highly regarded system. If you can afford it and can afford the space loss, then it's worth having a shot with RAID 10. So that pretty much sums up all the different RAID levels that are most common and some obsolete. If you like this video, feel free to give it a thumbs up. If you have any comments about any of the things I've talked about today, feel free to let me know. If I said anything wrong, feel free to correct me, and I will see you guys in the next video.